Alright, so this is a general acceleration problem. So we have a car, it's going to travel some distance d, and of course we're going to want to know what that distance is, and some of the other things that we know about it. The initial velocity is 0, so it's starting from rest. The initial time is 0, so it's starting at t equals 0, and we know that the weight of the car is 9,800 newtons. So right away we can, without doing anything else, we could figure out the mass of the car. Let's do the mass of the car is going to be the weight of the car divided by 9.8. And I've arranged this to make it quite simple, meters per second squared. So 9,000, it turns out to be 1,000, right? So 1,000 kilograms. So a car that weighs 9,800 newtons has a mass of 1,000 kilograms. And let's say that we apply a force. The car's engine, anyway, applies a force, and of course it's going to apply a force in this direction. So let's say the force is measured to be 2,000 newtons. All right, 2,000 newtons. So that's the force of the tires against the road is 2,000 newtons. So what I want to do is figure out, well, first of all, how far does the car travel? We're going to accelerate the car because the car has a net force acting on it. Here's the mass of the car. We can figure out the acceleration, right? Because F equals ma, right? We know that. That's Newton's second law. F equals ma. Okay, we use this all the time in classical mechanics. So the acceleration is going to be the force divided by the mass. And so we know that, right? It's 2,000 newtons divided by 1,000 kilograms. And so it's an acceleration of 2 meters per second squared. So now that we know the acceleration, let's say that the car accelerates for a time where when it gets to this point right here, the final position, let's say the time is I don't know, how about the time final is 4 seconds. Okay, so we accelerate at 2 meters per second squared for 4 seconds. So the question is, how far does the car travel? Right? And so we know the time. The time is 4 seconds. Time is 4 seconds. We know the acceleration is 2 meters per second squared. And so we have a general equation. See, this is a general acceleration, right? We know that the distance, how does the distance change with time when something is accelerating? It's 1/2, whatever that acceleration is. Remember, it's only for free-falling objects that the acceleration is 9.8 meters per second squared, right? That's just for something that's falling. This is something that's traveling horizontally, times the time squared. All right, so the distance is going to equal, let's go ahead and we'll do that over here. It's going to be 1/2, and our acceleration is 2 meters per second squared times 4 seconds, but we square that. And notice this second squared cancels this second squared nicely. And so we have, let's see, what would that be? It's just, I don't even need the calculator, because this 2 cancels this 2, and so it's just 4 squared, which of course is 16. So it's going to be, it traveled a distance of 16, and the only units that are left is meters. So it traveled 16 meters, right, because 4 squared is 16. Another thing that we could do if we want to expand this problem just a little bit is we could figure out the final velocity. What's the velocity right at this point when the time is equal to 4 seconds? So it's, the time is 4 seconds. It accelerated at a rate of 2 meters per second squared. So we can use the other equation. So this is the equation that relates velocity. I'm sorry, this equation relates distance to time when something's accelerating. But there's another equation that relates velocity to time. So it's the acceleration times the time. And so so we can now just plug this in. So this is it's accelerating at a rate of 2 meters per second squared, right? And the time is 4 seconds. 4 seconds, right? And so this seconds cancels one of these, leaving us with meters per second. And so the final velocity is just going to be 8, right? Because 2 times 4 is 8, so it's going to be 8 meters per second. So that's the final velocity. All right, and this is the distance that the car traveled in that time. All right, very good.